Now let's add some realism to our universe here. We have a few tricks that we can use to make exponential growth models more realistic, but fundamentally they are flawed because they are unconstrained. Now, let's add a constraint to population growth that I think that you'll find very intuitive. That is what our model here that I want to cover is constrained population growth, oftentimes called logistic population growth. We're going to add here a parameter that is going to cap the maximum population size for our whatever population it is that we're modeling. So again, we've got the change in the population by the change in time. How fast is this population changing and in what direction? And we're going to start off with something that looks very familiar, and that's population growth times the population. So we have to have new individuals coming from somewhere, and we're inheriting, in a sense, our exponential growth here. However, we know that it's flawed, so we're going to add something realistic to cap the growth. And that's something that you might know or have heard of in a high school biology class called carrying capacity. This is a parameter that caps, as I said, caps the maximum number of individuals, and it can represent many different things. I find the most familiar way to think about it is that as a resource limitation on the dynamics of any population. So, as I said, sometimes this will be called logistic growth, and that's because of the shape that the population growth takes over time. And sorry, I'm going to squeeze my population size in here, and what happens is this population dynamic will have an exponential growth phase. It'll have an unconstrained growth phase if you just plug in some parameters here. But as you start to reach the parameter k, the population growth rate will flatten out. And many organisms follow this kind of population growth. For example, after a clear cut or sometimes after fire or other kinds of events that free up a resource, say light, oftentimes limiting for tree populations. You'll have a system where you have exponential growth until the canopy starts to close and light becomes more limiting, in which case we start to have a flattening.